In this video, we'll look at practical aspects of directory-based protocols. Main memories in big systems are really large, and so are the number of processors. If we had one bit for each memory block recording which of any processor in the system had a copy of it, we'd have a tremendous number of bits. What can we do to cut down on the amount of storage required for the directories? Well, we've already seen that we wouldn't have the directory at one node. We'd have a directory distributed so that each memory that contained a block of memory held the directory entries for that block. We have to make sure that there aren't too many transactions each time we read or write a block, so we need schemes to optimize that. We need to decrease the number of transactions each time a protocol is invoked, and we need to make sure that not too many of those transactions are on the critical path. And then the issue I talked about at the beginning, directory storage requirements. The number of presence bits grows with the number of processors. Let's suppose that we had a 64-byte block size and 1,024 processors. How many bits are there in each block of memory versus number of bits in the directory? That'll give us a good idea of what the overhead of the directory-based scheme is. In a directory-based scheme, we locate all information about copies in the home node, that is, in the node that contains the memory that we're keeping track of. This works as well as a centralized scheme, works just the same as a centralized scheme, but it does have the property of being distributed. We also want to make sure that we don't need too many memory transactions to keep the directory up to date. Note that traffic on a write is proportional to the number of sharers, and the reason is because when you make a write, you need to go around and invalidate all of the other copies. So if there are a lot of copies, you need a lot of messages. There's also latency to this, but you could issue invalidations in parallel. That is, you could invalidate one copy, then another copy, then a third copy, without waiting for the inv-act to return from the first one. But you only go ahead after all of the invalidations have been acknowledged. Now in a few minutes we're going to see that we don't have to keep a full bit vector to record where the blocks are, but for now let's assume that we have a full bit vector. How can we make that full bit vector scheme use fewer bits? Well, the first thing we could do is increase the size of cache lines, because every time we do that, we increase the size of a memory block, so we decrease the number of blocks that there are in main memory for any given quantity of main memory. Or we could use multiprocessor nodes, where all we do is record which multiprocessor node a block is cached at. That still scales as PM, which is proportional to the number of processors times the size of memory, but that's only a problem for very large machines. For example, let's take the case where there are 256 processors and 4 processors per cluster. So how many clusters then do we have? Let's assume the line is 128 bytes long. What percentage overhead is there from the bit vectors? That is to say, how many bits do you have in the data line of the cache versus the number of bits that are devoted to the bit vector? Another thing we could do is eliminate the need to store 1 bit per processor in the system. And that would say that instead of keeping 1 bit to record whether a particular block is cached at a particular node, we make the entry contain pointers to the nodes where this block is cached. And that means that if you have a lot of processors, let's say if you have 1,024 processors, your bit vector length would be 1,024 bits. But you could use 100 10-bit pointers and still save space. Well, you're not going to need 100 pointers for each cache line. You might need 100 pointers for a few memory blocks, but you could have a little overflow area that dealt with that. And so you could get by with a rather small number of bits in a directory entry, just room enough for a few pointers, let's say for 2 or 3 pointers. We also need an overflow strategy, and that's why I said we need a little overflow area in case there is a block that has more copies than pointers will fit in the directory entry. But that should be fairly rare, and we only need 1 overflow area, so it still doesn't use so much memory. Another way of doing it is to reduce the so-called height of the directory. The number of memory blocks needs to be way larger than the number of cache lines because memory is way larger than cache. So most blocks, the vast majority of blocks in memory, won't be cached at any particular time, so we don't need directory entries for them unless they're cached. The way we could do it is, instead of having a directory entry for each block, we could have the directory entry itself be organized as a cache, which would be keyed on block number. So you look up the block number in this hash table, and if there's a hit, then you read out the bit vector or the number of pointers or whatever you use to keep track of where all the entries are. So far, we've talked about how a memory-based directory scheme is organized. Now let's talk for a minute about a cache-based directory scheme. In a cache-based scheme, the home node holds a pointer to the first cache that has a copy of the block, and then the copies are linked together via a distributed list that weaves through the caches. Each cache has a tag that points to the next cache on the list. When there's a read, the processor adds itself to the head of the list. On a write, it makes itself the head node on the list and then invalidates the rest of the nodes. Of course, all the invalidations need to be acknowledged. On a write back, the node just deletes itself from the list, and that means that the other nodes on the list need to be linked together around this node, so it just removes itself from the doubly linked list, essentially. A disadvantage of doing things this way is that every single operation requires communicating with at least 3 nodes, and the more sharers you have, the greater the write latency. But that's actually true even in a memory-based scheme, because you have to go and validate all those entries one by one. Synchronization is needed to make sure that multiple nodes don't manipulate this list concurrently, and synchronizing in a cache is a little bit more trouble than synchronizing in main memory. But on the other hand, the directory overhead is small because your directory entries are weaved through the cache lines, so they're just an extra pointer or two per cache line. That's the only overhead there is. Another advantage is that when there's invalidations to take place, each sharer invalidates, let's say, the next node on the list. It doesn't have to do a lot of invalidations, so it's not tied up for a long period of time. The IEEE-SCI, or Scalable Coherent Interface, formalizes protocols for handling cache-based directory schemes, and we won't have time to get into them in this course because they're quite complicated. Basically, they're simple, but there are a lot of race conditions that need to be dealt with, and that means that there are a lot of special cases that need to be considered.